Welcome to this explainer. You know, we all use laptops, smartphones, and tablets literally every single day. We type, we click, we watch, we game, and we completely take for granted the absolute miracle of engineering that makes it all happen right under the hood. Well, today we're going to fix that. We're peeling back the aluminum and glass to look straight into the brain of your machine, the central processing unit, or CPU. Just look at that number, 3 billion. The tiny chip sitting inside your laptop right now is likely performing upwards of 3 billion operations every single second. It's a number so incredibly massive, it's kind of impossible for the human brain to truly wrap around. But it's happening right now, silently, just to play this explainer for you. But, that begs a pretty massive question, right? What exactly is an operation? When we say a computer is computing, what is actually happening inside that tiny, fragile little square of silicon? To answer that, we've got to take a journey. We have to zoom way, way down from the laptop on your desk, past the motherboard, past the microscopic wires, all the way down to the atomic level. Section 1. The fundamental building block. Okay, let's dive into this. To understand the incredibly complex stuff, we have to start with the wonderfully simple. Everything your computer does, like every rendering of a high-def video, every massive spreadsheet, every AI prompt, it all boils down to a single concept, the transistor. A transistor is, well, it's just a microscopic switch. It only has two states. It can let electrical current flow, which we call on or a 1, or it can stop the current, which is off or a 0. That's it, 1 or 0. But here is the absolute mind-blowing part. Modern CPUs don't just have a few of these. They contain tens of billions of these microscopic switches, literally etched onto a piece of silicon smaller than your fingernail.
So you might be wondering, how do we actually make silicon do this? Well, silicon is naturally a semiconductor. That means it doesn't conduct electricity perfectly, but it doesn't block it completely either. To make it work for us, engineers do this process called doping. They alter the silicon's conductivity by introducing different elements. So if they dope it with phosphorus, they create what's called N-type material. If they use boron, they get P-type material. By cleverly sandwiching these materials together, engineers create these tiny transistors that can flip between a 1 and a 0 using astonishingly tiny voltages. It is an absolute masterpiece of semiconductor physics.
Moving on to Section 2, Mathematics of Ones and Zeros. Okay, so how do we use physical switches to do actual math? That brings us to logic gates. And this brilliantly illustrates how we bridge the gap between physics and logic. You see, a single switch, not very smart. But when you wire combinations of transistors together, you get logic gates. You can see the different ones here: the AND gate, the OR gate, the NOT gate, and the NAND gate. These take electrical inputs, those ones and zeros, and output a result based on very specific rules. We call this Boolean algebra. For instance, an AND gate only outputs a 1 if both of its inputs are 1. It sounds so incredibly simple, but I promise you, this is the bedrock foundation of all computer logic. From there, things scale up super rapidly. We take those simple little logic gates and combine them into massive, complex circuits. We build adders to actually perform arithmetic. We build multiplexers to act like microscopic traffic cops routing data around. We build flip-flops to actually store those ones and zeros as memory. And when you combine the whole shebang together, you get the crown jewel of the processor, the arithmetic logic unit, or ALU. The ALU is essentially the mathematical brain of the CPU, ready to crunch the numbers. All right, Section 3, the core execution cycle. So we've got the brain, right? But it needs a heartbeat. It needs a rhythm to do its work. This three-step dance is basically the fundamental day in the life of a processor. Step 1, fetch. The CPU reaches out to memory and grabs the next instruction it needs. Step 2, decode. It looks at that instruction and interprets what it actually means. Like, is it addition? Is it moving data? Then, step 3, execute. The CPU actually performs the operation using the ALU or other units. Fetch, decode, execute. Over and over and over again. But guys, here is where it gets absolutely crazy. When you buy a computer, you might see a spec that says, 3.5 gigahertz clock speed. That oscillator inside the CPU is ticking at a fixed frequency. 3.5 gigahertz means that simple fetch, decode, execute cycle we literally just talked about, it is repeating 3.5 billion times every single second. Billion with a B. The speed is so incomprehensibly fast that the biggest problem for the CPU isn't doing the math anymore, it's actually getting the data fast enough just to keep up. Which leads us perfectly into section 4, caches and fast memory. This brings us to the ultimate logistical nightmare. If you have a processor moving at billions of cycles per second, how on earth do you feed it data without slowing it down? Well, you use a hierarchy of memory directly on the chip itself. At the very top, we've got CPU registers. These are tiny, ultra-fast storage locations holding just 16 to 64 bits. This is the data the CPU is working on right this exact nanosecond. Just beneath that, we have cache memory, which is organized in tiers, L1, L2, and L3. L1 is the smallest but fastest, right there on the CPU core. L3 is bigger but slightly slower. The CPU stores frequently used data here, so it doesn't have to wait for the main system RAM. Because if the CPU looks for data in the cache and it's not there, which is called a cache miss, the entire blistering fast processor essentially has to just sit there and wait, and that drastically slows down performance. Section 5. Advanced Speed and Prediction.
Now, engineers absolutely despise a CPU sitting idle. To push speeds even faster, their first real trick is instruction pipelining. Think of a car factory assembly line. You don't build one entire car, finish it, and then start the next one from scratch, right? You overlap the steps. Well, the CPU does the exact same thing. Instead of waiting for one fetch-decode-execute cycle to completely finish, it overlaps them. So while it's executing instruction 1, it's already decoding instruction 2 and fetching instruction 3. This pipelining prevents the CPU from ever waiting idle. It turns it into a continuous flowing river of data.
Now, what's really fascinating about this slide is a concept that honestly sounds like science fiction: branch prediction. Imagine the CPU reaches a fork in the road, like an if-else statement in the code. Instead of stopping and waiting to calculate which path to take, the CPU literally guesses the future. It speculatively starts executing down the path it thinks is right. If it guesses correctly, boom, it saves massive amounts of time. If it's wrong, it just throws the work away. Amazingly, modern CPUs guess right more than 95% of the time. Interestingly enough, this exact speculative behavior is what led to the famous Spectre security vulnerability a few years back, because hackers actually figured out how to peek at that discarded speculative work. Wild, right?
Another brilliant hack is out-of-order execution. Normally, programs are written in a strict step-by-step order. But what if, say, step 3 is ready to go, but step 2 is still waiting on data from memory? Instead of stalling the whole system, the CPU will dynamically reorganize the tasks on the fly. It executes instructions the exact millisecond their inputs are ready, completely defying the strict program order. And it does all this just to ensure every single processing unit inside that chip stays constantly busy.
Section 6. Pushing the physical limits. We gotta talk about limits, because cramming all this power into a tiny space has profound real-world consequences. Let's trace this back to 1965. Gordon Moore made a famous observation that became known as Moore's Law. He basically noted that the number of transistors we could fit on a chip doubled roughly every 2 years. And for decades, this held true, driving the entire technological revolution we live in today. But look at the far right of the timeline there. Today, we're manufacturing chips at the 3-nanometer process node. At 3 nanometers, a transistor is, well, it's roughly 10 to 15 silicon atoms wide. We aren't just hitting engineering limits anymore. We are literally bumping up against the fundamental laws of atomic physics. Because of these physical limits, we've really had to adapt. We can't just make a single processor core infinitely faster anymore. Why? Because flipping billions of transistors generates an immense amount of heat and eats up huge amounts of power. So, we manage this by using multi-core processors. We put 4, 8, or even 16 independent CPU cores on one chip to run tasks in parallel. It's exactly why the incredibly efficient RISC architecture of Apple's M-series silicon allows MacBooks to run super fast while staying completely cool. On the flip side, it's also why high-end gaming PCs need massive heat sinks, thermal paste, and huge fans to prevent the CPU from literally cooking itself. And it's why giant data center server farms require industrial-grade air conditioning. It all comes right back to the heat generated by those billions of tiny switches. I absolutely love this thought. Every time you open a laptop now, you know exactly what that chip is actually doing. We've traveled from a single microscopic silicon switch doped with boron or phosphorus, all the way up to multi-core, incredibly predictive, deeply pipelined technological marvels that are executing billions of calculations every single second. So I'm going to leave you with this final question. Next time you're rendering a video or playing an intense game and you feel that warm heat venting out the side of your laptop, will you think of the billions of tiny atomic-scale switches furiously flipping on and off inside? It really kind of changes how you look at the devices we use every single day, doesn't it? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll see you in the next one.